So topic 5 is all about partial differential equations. And in particular, most of the time in engineering, in chemical engineering, when you're talking about partial differential equations, you're talking about things that vary with time and with space. So I know all of you are supposed to be in fluids before, so you've seen the Navier-Stokes equations, right? Maybe you've done some form of heat transfer, I don't know, that also has a set of equations that look similar to that. So I'm going to go ahead and write out what these equations look like so it can set you up for thinking about the boundary conditions and taking numerical derivatives and putting these equations into MATLAB like we're going to have to do. So in general, you have the transport of momentum, heat, and mass, and they're all written in very similar looking equations. So your momentum equation will be rho times your total derivative, capital D V dt, that's your total derivative of your velocity, is equal to minus del dot your stress tensor minus the gradient of your pressure plus rho times the vector of the acceleration of gravity. All right, so this tau is your stress tensor. Right, so that's your conservation of momentum, that's your momentum transfer equation. You can also write down your heat transfer equation. So your heat transfer equation is rho Cp, the time derivative of temperature, is equal to minus del dot phi, where phi is your vector of heat flux, and that's in units of watts per square meter. And of course, you also have other heat source terms that could be in your heat transfer equation. Right, so that's heat transfer. And the previous one was momentum transfer. And then you also have mass transfer, or dilute mass transfer. Which is the equation I'm about to write. And that would be the partial of the concentration of species I with respect to time is equal to minus del dot J of species I, where J is your material flux, and that's in units of moles per area time. And you have other terms that could appear in these equations like reaction terms. So that's like F for species I, which is a function of time and concentration. Sorry, that F is not a vector. So these equations, they all look the same, right? You have your time derivative on the left-hand side. You have some del dot some flux minus del dot some flux, and you have other terms that could affect the balance of whatever you are bookkeeping for in those equations, right? Now, each one of these scenarios, you have some sort of constitutive relationship, right? So Isaac Newton is a pretty smart dude, and he came up with like the relationship between your stress tensor and your the gradient of your velocity, right? So that's minus some constant mu times del v plus del v transpose, right? And that's for Newtonian fluids. And of course, mu there, that constant is your viscosity, right? You have Fourier's law, which says that your heat flux is equal to minus your thermal conductivity times the gradient of your temperature. That's Fourier's law. And for mass transfer, the material flux J for species I is equal to minus the diffusivity of species I times the gradient of your concentration of species I, right? That's called Fick's law. Now these constitutive relationships, they don't hold true forever. They're not as fundamental as mass balances, right? So they're not God-given. They're based on general assumptions, which hold generally true. So there are a lot of fluids that are Newtonian fluids. There are a lot of scenarios where fixed law of diffusion holds. And so your flux is equal to the gradient of your concentration, or proportional to, right? Or Fourier's law, where your heat flux is proportional to the gradient of your temperature. They're not always true, but they're typically true. So a lot of times we'll take these constitutive relationships, we'll plug them into the mass, or not mass balance, the bookkeeping balance equations that we have above, and get these super famous equations that we have at the bottom, right? The first one being the Navier-Stokes equations, which I know that you all have seen in your fluids class, but also there's a heat transfer equation, and there's a dilute diffusion equation, right? Last thing before we go, don't pack up. In this heat transfer equation, this Q dot, this is a volumetric heat flow. That's in watts per meter cubed, right? It's on a per volume. And this F term here in your mass transfer equation, those are like reaction terms. So when you watch the screencasts about boundary conditions, etc., you'll need to know, like, okay, I need to know what a flux is, and a flux is approximately equal to minus d, or not approximately, it's assumed to be equal to minus d times your spatial gradient of your concentration.